Okay, so what is the problem here? We're looking at finding the force acting downwards, which is equivalent to the weight of the performer. So first you need to have the poles, right? So start with the picture. So you got the poles, there you go, two identical poles. It says when a tightrope walker is at the middle of the wire, there is some sagging on the wire, obviously, because the person is standing in the middle, right? So if I were to just kind of draw the horizontal, I'm going to draw the horizontal. The person, that's not the wire, that's just the horizontal. Now I'm going to draw the wire with a green pen. And it says when the person is standing right here, like that, the rope starts to sag at 9 degrees with respect to the horizontal, each half. So it goes like that. And they are identical. So you have a triangle right here. So now you've had a triangle, and these ones, that's 9 degrees each. 9 degrees. It's just a little bit of sagging, okay? So what do we know? We know that the tension in the rope, the wire is stretched when the tightrope walker is at the middle of the wire. The tension in the rope is 550. That would be the entire rope. Is that what you're understanding? It didn't say each half. So that means the total of these two, and let's call this one FT1, and let's call this one FT2. So what can we say here? What is that 2550 newtons? That's the... So how do we convert that sentence into a formula now? What can we do with that number and the FT1 and FT2? It says that the tightrope walker, when it's in the middle, the tension in the rope is that. So we can say that FT1 plus FT2, that's the wire. That's the entire wire. It just happens to be sagging. They're not two different wire. This should be equal to 2050. Let's write that down for now. That is what we know.
If we're splitting the 2550, then the answer goes wrong. I did it both ways.
Yeah, it might have been misunderstood, but I'm looking at this now. Don't worry about the answer key. So when the tightrope walker is at the middle of the wire, the tension in the rope is 2550. How are you understanding that one? The tension on the entire rope, right? Yeah.
The tension is like goes up like FN. So I get it. So the FN is
There's no FN here.
the
FT
is upward, I guess, and then the FT is downward.
The FT.
Upward.
There's two things happening, right? So if I were to just draw one half, there you go, 9 degrees here, okay? This is the FT1 of Y, upwards. The actual wire is the FT of 1, pulling this way. The arrow will make it, will make sense. This one should be pulling up. Okay, and this one here is pulling the person sideways. We call it the FT1 of X. Now, I'm reading this thing here, and it looks like the tension in the rope, it says, is 2550. That is, how many ropes are we talking about? One rope. So that should be the case here. It didn't say each half the rope is 2550. So I don't know what the answer key is. I'm not going to worry about that until we actually go through the problem solving process. Does that make sense? In the wording, I'm going to change that wording because this one actually came from a book. And I don't like the wording there. If the answer key is a different answer key than what we get, something's wrong with the wording. So because right now it looks like the rope is 2550 newtons, okay? It didn't say each side, so that's what I'm gonna stick with. Otherwise, I'm gonna clarify that here. Each side of the rope is experiencing this much tension, then that would be a different question then. Okay, so I'll stick with this one here. So we know that FT1 and FT2 should be the same because the person's in the middle and the angle is the same. So therefore, that means therefore, FT1 equals FT2 equals what? 2550 divided by 2 is 1275 newtons. Make sense? Okay? So let's now split it in the X and Y component. You're looking at the force acting downwards. We don't really care about the X component here, but I'm going to write it down anyway. Okay? So the net force on the horizontal is FT1X minus FT2X equals 0. It's not part of the question. I'm just writing it down just to get used to making sure you guys are okay with that. No questions about that? And then the Y component, this is what we're actually solving for. Can you tell me what you have for the net force on the Y? FT1 of Y plus FT2 of Y minus FG. You notice the pattern here? They're almost all the same. Equals 0. So what are we looking for? We're looking for the FT1 of Y, which is the same as FT2 of Y, correct? Okay, so FT1Y plus FT2Y equals, what's our FG? Oh, that is what we're looking for. That is equivalent to the weight of the performer. So what's our FT1Y? We can now solve for that. We know the FT1 is 1275 newtons. We know that's 9 degrees. Simple trig now, right? So we now have the hypotenuse. We're looking for this side right here. So opposite over hypotenuse. We can then just go sine of 9 degrees equals opposite FT1Y over 1275, because we know FT1 is 1275. Okay, so FT1Y is 1275 times sine of 9, and this should be 199.5 Newton. Call it 200. So FT1Y is 199.5, but that's only one side of the rope. So therefore the FG, which is double that, will be about 399 Newton. That is the weight of the person, which would be, person is 90 pounds. It's a very small person. You know what? Have you seen those people who work in the circus? The ones that do trapeze? They have to be very, very skinny and small, right? Because they gotta make sure that they have a rope and it doesn't break. Now the weight has nothing to do with that. They just have to use a stronger rope. So this is the answer. On the back, it's double that, isn't it? Yeah. So I'm gonna change that because that doesn't make sense, because the rope is one rope. So that should be 399. And again, I'm gonna forget that, and I'm gonna make the book again next time. So I gotta get to the computer and change that. So that's that. We should change that right now. Should we do the next thing? Are you okay with the same angle? Shall we move on? I'm gonna just make myself a note because I'm gonna forget again. Change number 5, wording on page 8. Okay, now this is the one we started yesterday. Any questions about the FBD? This is the FBD. These are the FBD equations. Are we okay with those? Yeah? We need the FT1 and FT2. Okay, so what we're going to do is we're going to now expand the equations. So let's expand on the x-axis. Okay, so that's equal to 0. So we know that FT2x equals FT1x. Tell me that makes sense. Yes? Let's expand on the y component. So we got ft1y plus ft2y equals fg. Doing this step by step. Not gonna miss a step for the first example, okay? Is that good? So can we expand this even further? Remember, this is what we're dealing with for ft2x, that diagram. So we need to keep going back to the original triangle. So what we know, that's 80 degrees. That's the inside angle, yes? That's 80 degrees. So how do we find the ft2x? This one. That's called the opposite, correct? So we have opposite and hypotenuse. What's that in terms of SOHCAHTOA? We're using SOHCAHTOA now. So SOHCAHTOA. Opposite and hypotenuse is sine. So now we have ft2 sine of 80. Okay, just so I can expand on this one. Okay, I'm going to write it down right here. So I don't want to miss any step at this point. If I go sine of 80, look at this. Sine of 80, I'm using the SO, right? Is equal to opposite ft2x over hypotenuse, which is ft2. Is that okay? So if I'm looking for ft2x, that's all I did. ft2 times sine of 80. Is that okay? Trick is right there. Cross multiplied. That's where that came from. Okay? So ft2 sine of 80. And this is equal to, now how do we deal with the first triangle? ft1 of x. Again, this is the triangle. This is the angle is 65. You go opposite over hypotenuse. That's also sine, right? Is that okay? Sine of 65 is opposite ft1x over hypotenuse is ft1. So here we go. You see how it says ft1x? That's ft1x right there. You just multiply. Okay? So this becomes ft1 sine of 65 degrees. Is that okay so far? I want you to try to do that with the y component. So ft1y using the same picture that we have up here. So there's the ft1 of y right here. So same angle. What do we do? Adjacent and hypotenuse. What's that? Cos. So all we need to do is go ft1. The y, that little subscript y, that means cos of, what is this? 65. Is that okay? And you look at the second picture, ft2y, adjacent over hypotenuse. Ka. Again, it's cosine, right? Plus ft2 cosine of 80. You remember when we were doing vectors and I taught you the strategy for vectors. If the angle is taken from the x-axis, this is not the x-axis. I can do the same strategy if I'd like. If this is 80, I can do the 10. And this will become, for y, it will become sine of 10. That works again. And here, you see, because the angle is 65, what would be the outside angle? 90 minus 65. 25, right? You can also go cos of 25 for x and sine of 25 for y, as long as you're doing the trigonometry. So this is now the ft2y, and how do we expand on the fg? Fg, we know the number, so we're not looking for that. I'm gonna just put 535. You know where I got the 535 from? The climber weighs 535. That is the Fg right there. Okay? Weight is Fg. So that is what we know so far. Now, do we have anything in common here? Well, we know that there's Ft1 and Ft2 on both sides, and we need to somehow come up with one unifying equation. So here's what we'll do. Let's come up with the number as much as we can. What is sine of 80? Grab your calculator. Check you're on degree mode. Okay? So, what is sine of 80? 0.984. So because I have nothing in common right now with these numbers, you know what? Instead of putting numbers, I'm going to save that until the end. So here's what I'm gonna do, and it doesn't matter. I'm gonna pick this one because it's simple. I'm gonna isolate FT2. I could also isolate FT1, doesn't matter. I'm gonna pick FT2 for this, and look what I have. This will become FT1 sine of 65 divided by sine of 80. That's gonna give me less calculation. Okay? So now I can pick up my calculator and solve for this. So FT2 will become, look, sine of 65 divided by sine of 80. And I have 0.92. So this will become 0.92 FT1. Does that make sense? So I have this, that's as simple as it gets on the x-axis. So now I'm going to take where I find FT2, and I'm going to substitute FT2 into the y component, which is right there. Do you follow the technique? Now it's just math. We've done the physics. Now this part's just math. Okay, so here's what I'm going to do. I have cos of 65 here. I've got FT1. We don't know what FT1 is, but I know FT2. I'm going to leave it until the end, so I'm going to just rewrite this. Cos of 65. Let's actually do that right now. Cos of 65. I'm going to put numbers here. Okay, so this is 0.423. So 0.423 FT1 is what I have. Plus, you see this FT2? That is the entire FT2 now. Do you follow? I'm getting rid of FT2 so that this equation contains only FT1. You know when you have an x and y in an equation and you're solving for x, right? You eliminate the y and you just now solve for x and then go back and solve for y. This is exactly the same strategy. So this FT2, look at this. That's this now. Do you see it? Do you see it? FT2 right there. This is FT2. It's this whole thing. So now I'm going to go 0.92 FT1. But I still have cosine of 80 there. You see it? This thing here, that used to be FT2 from here. But I still have the cos of 80, and this is still equal to 535. Make sense? So now what we could do is put everything in numbers. So here you got 0.423 FT1, because that's the proper way in math, is that you start with a number and an unknown variable. So it's like 2x. This is what that is, 0.423 FT1. Plus, now I can solve for that cos of 80. What's cos of 80? 0.17. But this is multiplied by 0.92. These are all multiplied. Okay, so I'm going to multiply it by 0.92, and this is now 0.159 FT1. And this is equal to 5. One more step. What do we do now? Solve for FT1. That's the only variable. We have combined the like terms. Solve for FT1. That's the only thing that's unknown. So we have 0.423. That's that number. Plus, because it's added, 0.159 equals 0.582 FT1 equals 535. Is that okay? Go one step ahead of me. Now let's look at the numbers that we got. So I'm just going to compare the two. FT1 is greater than FT2. Let's go back to our picture. FT1 is here. It's a greater tension than that one. So what does that tell you? If the rope is going to break, where is it going to break first? FT1 has got more tension force. That's what that means. And it makes sense because this one here, the angle is sharper. So if you're looking at the actual diagonal force, this one here is going to experience more force than that one. Okay, so if you want to even it out, you're going to move this person in the middle to spread it out. And that is similar to the example that we talked about yesterday with the seesaw. If you're closer, then you're actually going to be changing that equilibrium, right? Check the answer in the back, see if that answer matches with this one. It's the same answer. It's not. 846, 844.5, 845, and the other one is 918, and we got 919. Looks like someone's rounding off. It's the exact same thing. Okay, so yeah, you can do that. And you'll get the same answer. I was just writing every single step here, so that's why it looks long. So it doesn't have to be like that every time. So what you did is you simplified this side instead.
I mean, I kept it at the above the one at the
This equation, this one.
Yeah. The F2 is equal to T1
Sine of 65. Yeah. Over sine of 80. Yeah, you can keep that. And then you can keep the whole thing instead of having this number here. And then you can put that over there. You'll get the same number, right? Yeah. Yeah. It's the same thing. Except when I calculated here, you calculated here.
Yeah, but I think it would be more exact because we're rounding up 0.9.
Oh yeah, I see. Because here I already rounded off here. But if I saved it until the end, then you're only rounding off once. Yeah. Okay, but is the strategy, does that make sense? The math part, that is just, calculation differences. But what you need to understand here is you're looking at one equation. In the end, this is the equation that you came up with. That one equation united the x and the y component. So you'll see that that is something that we're going to be doing when you deal with angles that are different forces. So here's what we did. First, we split it up into the x and y component. Okay, you split it up, completely different, and then you put it back together. That's what we did here. You separated them. It's like when you're trying to fix a car, for example, you gotta take out the machineries first. You gotta take out the parts and then fix it, and then you gotta put it back together. And that's what we did. We split it up. We did what we can do. Okay? We fixed it up. We put it together in one single equation, and that solves the problem. So, shall we practice that strategy? Split it up, fix it, and put it back. Have you guys ever done that as a kid? Something's wrong with the toy, right? How would you fix it? The flashlight's not working. What do? You open it up, you take out the battery, you fix the part, and then you put it back. That's how you fix anything, right? Something wrong with you, you need surgery. The doctors will then open you up, split up the parts that you need to get fixed, and then put you back together. That's the same strategy. All right, let's try this one. Number 7. You want to try this or you want to see another example? One more time? One more example, okay? Okay, so you have this person, police officer, 72 kilogram. So what does that give you? Right away, you have a force right there. This 72 kilogram gives you Fg. Fg is m times g, so you got 72 times 9.8. That is not the weight, but you can get the weight right from there, right? And that gives you 705.6 newtons. So that we know for sure. So I'm going to just write down the force that is going down. That's your Fg. 705.6. Then the question is, find the tension force on each side of the cable. Okay? So this is pointing up this way at an angle, pointing up that way at an angle. That's what we're looking for. So let's call that Ft1 and Ft2. That's the unknown. Okay, strategy number 1, split it up. Can you write down the x and y components? So what I find easy is that when you're comparing or splitting the x and y component, write them side by side. So that way you'll see, you have a visual guide of what do they have in common, right? Okay, tell me what's on the x component. Net force on the x. Those ones. Ft1x minus Ft2x equals 0. Guess what? It doesn't matter what order you call it. You could go Ft2x minus Ft1x is still equal to 0. Excuse me. So Ft1x equals Ft2x. Right? What do you have in the y component? You will see that the y component is almost always the same because we're still dealing with similar questions. So you got Does that make sense? You see, you're writing equations based on the event, and which is based on the free body diagram. Now what? You've split it up. Now you're going to expand it into pieces. Look at your triangle. I can pick this triangle here, or I can do it this way as well. Now you see the angles already from the x-axis. I'm just gonna go Ft1 cos of 35 and do that, which is equal to Ft2 cos of 48. Okay? Ft1 then becomes Ft1 sine of 35 plus Ft2 cos of 35 equals 705.6. I'm going to try not to round off this time. Keep it at 705.6. Okay. Now what? You're going to start putting it together now. I'm going to leave this to you. So I'm going to give you a couple of minutes to go from here. Okay, go ahead. I want you to try this. So here are the answers, so you can check your answers.